Well, so this is the topic we have been discussing for the last couple of lectures, volume integral. So surface integral we already have covered. So volume integral, in case of volume integral, so what is the difference? Only the region of integration will change. Instead of a surface, three-dimensional surface, here we will have a portion of the space. And the function defined in that region could be a vector function or a scalar function. Okay, so depending on that, we will get different type of volume integrals. The basic idea is similar. We will divide the region into finite parts, and a typical region is shown over here. The volume of that region, so shape of this region is considered to be cuboidal, and its volume is taken as delta V, and within that delta Vk, kth region, kth smaller region, and its volume is given by delta xk, delta yk, and delta zk. Okay, and from that region we'll take a point, let us suppose pk, and the coordinates of that point, let us suppose xk, yk, zk. And at that point, we will calculate the value of the given function, either scalar or vector. And then we will multiply that value, and let us call that value to be equal to ak or phi k. And let us multiply that value with the volume of the elementary region. And then so this is our integration element for the kth region, either this one or phi k delta vk, if the function is scalar. Then we will form the sum elementary for all the elements, for all the smaller regions, and then finally we will take the limit. And if this limit exists uniquely, it is called the volume integration of the associated function over the region V. Okay. Now here is one example. We have to show that volume integral of phi over dv is equal to 1 by 4, where phi is the scalar function 15xy, and v denotes the region bounded by the planes, this one x equal to 0, y equal to 0, z equal to 0. So these four planes will determine a closed region in space, and on that region we have to find the volume integral of the given scalar function 15xy. So let us see how to solve this problem. So this is my coordinate system. X equal to 0 means yz plane, y equal to 0 means z x plane, and z is equal to 0 means xy plane. So that means coordinate planes, and along with that we have another plane, x plus 4y plus z is equal to 2. So x plus 4y plus z is equal to 2. So therefore
minus z equals to 2.
Minus z is there. No, this is x plus 4y plus z. So some noise is coming. Yeah, so x plus 4y plus z equal to 0. So that means x by 2 plus y by half plus z by 2, this is equal to 1. So this is 1 point. So this is one of the points, 0 half, this one, and 2 is similar. So this is the plane which is bounding the region x 0 y z, and this is your a b c plane, And the region under consideration, so what is our V is quite clear from here. Now how to, acha, so what is the function phi is equal to 15xy, I think 15xy.
Yes, sir.
15xy. And how to, you see Z is varying from, so you can understand the region under consideration. Z is varying from Z is equal to 0. We will move from xy plane to this one, x plus 4y plus z equal to 2, this plane. Z will vary from this. And to determine the limits of x and y, we have to look at the projection of this region on xy plane. So what is that? Let us have a look at it. So on the xy plane, 0 y and z. So this is the plane, this is the line on, this is the line given by x plus 4y equal to 2. That means this is 1 point, this is your 2 0, and so therefore first we have to cover, we have to choose the limits in such a way, we have to cover this projection R. This is your R. Yes.
No, sir.
Yes.
It's okay, sir.
So first we have to cover the projection, so the region which is obtained by projecting the plane ABC on xy plane, this region R, by choosing the limits of x and y. So how to do this? We will look at the, typically as per our convenience, we will look at the region from this side. So therefore it turns out that x will vary from, as x will vary from 0 to 2, y will vary from 2 minus x by 4. Yeah. So therefore over V phi dx, phi dv rather, dv, this is equal to x equal to 0 to 2 dx. This we will perform later on, and y will be from 0 to
2 minus x by 4.
2 minus x by 4. This is y integration, and then for each points on this region R, so how Z will vary? Z will vary from 0 to this plane.
2 minus x minus 4y.
2 minus x minus 4y.
Yes, very good. 2 minus x minus 4y, and phi, control Z, that is phi is equal to 15 xy dz. Note that while this is repeated integration, we have express this volume integral in terms of repeated integrals, and in evaluating the repeated integral while performing integration with respect to one variable, other variables we will always consider as constant. So therefore for performing, first we will perform the z integration. While performing z integration, we will consider xy to be constant. So therefore 15xy will come out of the integration operator, and eventually we'll get x is equal to 0 to 2 dx, y is equal to 0 to 2 minus x by 4 dy, and 15xy will be there, and integration will be z, and limit will be 0 to
2 minus x
0
minus 4.
2 minus x minus 4y, and then we are left with a double integral. X is equal to 0 to 2 dx plus y equal to 0 to 2 minus x by 4. So we get 15, I can put outside, xy into 2 minus x minus 4y, and now we will perform y integration. So while performing y integration, you consider x to be constant. Okay, absolute constants are already there, 2 and 4, and along with that we will consider x to be constant, and then you evaluate these two iterated integrals, so and find the result. It should match with the desired result, which is 1 by 4. So just calculate it and confirm. You should get 1 by 4.
Yes, sir.
Yeah, so are you getting 1 by 4? All
Yes,
of you?
sir.
Okay,
Yes.
so therefore,
Please show the question.
Acha, yeah. Okay, this one, question number 1. And now we will solve question number 3. We will solve question number 3. It is a volume integral involving a vector itself. You see A, and the region is also a bit tricky. We have a parabolic region on the xz plane. Okay, so the vector under consideration is xi plus yj plus zk. This is basically the position vector of a point. Okay, so let us solve problem number 3. X equal to 0 to 2, y equal to 0 to 6, and z equal to x squared to 4. Okay. So we have to evaluate the volume integral A. This is a vector dv where A is equal to ix plus jy plus kz, and the volume is given by bounded by x is equal to 0, x is equal to 2, y equal to 0, y equal to 6, and z equal to x square, z is equal to 4. So what is the region of integration? Let us try to understand. So this is these are my coordinate axes. 0, x, y, z. Now, okay, so x will vary from 0 to 2. X equal to 0 means yz plane, and x is equal to 2 means zx a plane parallel to yz plane at a distance 2. And 6, let us suppose this y equal to 6. So this region is covered. Now what we have to do, so z is equal to x square. Z is equal to x square. That means, so it will be something like this. Parabola will typically look like this, and it will be no, control Z, this part is not there, this part will not be there. This part is there. This one is the paraboloid, and it will z will basically, and z is equal to 4 means you have a point over here and something like this.
Sir, for z is equal to x square, doesn't it passes through origin and symmetric about z axis?
Z is equal to x square means for each values of x z, there will be two values.
So just like y is equal to x square.
Yeah, z is, so is
Yes,
there
sir.
any?
Sir, the
Is it-
parabola
Pass to the
came upward, not downward, sir.
Yes, sir.
Yeah.
Passes through origin and
Passing,
symmetric.
yeah. So there is a
passing
mistake.
through origin is symmetric about that.
Yeah. Very good. So I have to correct the figure. Yeah. So it will be something like this. It will be something like this. and then there will be another plane which is at z is equal to 4. Z is equal to 4 means a plane. Acha. So something like this actually. It will be basically something like this. It should pass through. I cannot move beyond this point. So therefore it is something like this. Yeah. So it will be okay. And then above this is z is equal to, this one is z is equal to x square, and above this we have z is equal to 4 plane. This one. This is your z is equal to 4. So yeah, so therefore z is varying from this plane. Z is this surface, z is equal to x square to z is equal to 4, and x.
Sir, at x is equal to 2 and y is equal to 6, in the xy plane there will be a rectangle form. I think the surface
Here, then the projection of this region will be something like this. X will vary from 0 to 2 and y will vary from 0 to 6. So therefore this region will be the projection of this region on xy plane will be this. This is your R, 0x y. It will move from, in the x direction it will move from 0 to 2. Oh, y direction it is much larger. Yeah, let's see up to this, and this is your say 4. This is your, excuse me, yeah, this is your R, 0x y, and this is 0 2 and no 20 06. So this is the projection of this three-dimensional region enclosed by z is equal to x square and z equal to 4 on xy plane. So therefore your volume integration over this will be equal to 0 to 2, x equal to 0 to 2 dx, y equal to 0 to 6 dy, and z will be x square to 4. 4 is lying above. X square to 4, then ix plus jy plus kz dz. So you can now integrate it one by one using this.
96, sir. 96.
26 will not be, you will get a vector.
96, sir. 96.
No, you will get a vector.
Sir, answer, sir. Total answer, sir.
No, total answer will not be a scalar.
Final, sir. Sir,
How
divergence, sir. Theory, sir.
No, this is not dot product. It is just vector integration, vector. Yeah. This is not divergence. You have to integrate it.
Answer will be in the form of I cap, J cap, and K cap.
Yeah, it will be a vector actually.
Yes, sir.
So what will be that vector? Just a minute. It will be equal to. It will be equal to x equal to 0 to 2 dx, y equal to 0 to 6 dy, and this will be equal to x z I plus yzj plus z square by z square by 2 k, and the limits are x square to 4. So z integration is done. You will get x equal to 0 to 2 dx plus y is equal to 0 to 6 dy, and if we put 4, we'll get 4xi plus 4yj, then this is 16 by 8k plus 8k minus, if we put x square, we'll get x cube I minus x square y j minus x to the power 4 by 2k. So now we have a function of x and y. We have to complete this double integral and you will get a vector. So can you tell me the answer? So let me just write 0 to 2 dx and y is equal to 0 to 6, and we have 4x minus x cube I, 4x minus x cube I plus 4y minus x square yj plus 8 minus x to the power 4 by 2k. So dy. And note that once again we will consider x to be constant while evaluating this y integral. So therefore we'll get eventually x is equal to 0 to 2 dx, and this is 4/3 x square, 2x square, 2x square minus 1 by 4 x to the power 4i this is the integral, and plus 4x, no, sorry, I am doing some mistake. What is happening?
So with respect to y, you have to.
With respect to y, I have to consider x to be constant. So it will be 4xy actually. xy minus x cube y j plus this is 2y square minus x square y square by 2 by 2j, and then plus 8y minus x to the power 4y by 2k, and the limits are 0 to 6. And once you put the limit, you will get absolutely limit for y, you will absolutely get a function of x, and then you perform the final integration and you will get a vector. So what is that vector? Do I have the answer here? No. So I think you can do it. You will just put x is equal to y is equal to 6. Y is equal to 6 in this vector, and we are left with a function of x, and then you will do the x integration and you will get a constant vector. So that is the answer. So therefore you see volume integration is not that difficult if we understand the region carefully. So what is the basic technique? So once we understand the region in space very carefully, then we will take a projection of that three-dimensional space on xy plane. Okay, and then on that projection that projection will help us to determine the range of x and y, and for each points on that range, on that projection, we have to look at the range of y, a range of z, that will determine the limits of x, y and z. And once the limits of x, y and z are determined, clearly determined, then we can evaluate the volume integral using iterated integral. These are nothing but integrals of a function of like the integrals of a function of single variable. Okay, so that is the technique, and I hope you will be able to solve the problems. And next we have
Sir, one should previously.
yes.
One
Sir, is the answer 24 in common I cap plus 4j cap plus 16 by 5 k cap?
Maybe I don't know. So you have to calculate. Yes. So
I
I
got
think
Sir,
this
something else.
is.
sir,
Some
sir,
slightly.
here if the z limit is somewhat complicated and it is hard to get the integration of z, so
Mhm.
can we do some changes to get the answer quick, like the
Yeah,
changing order?
yeah. That is also there. Probably those things are discussed in detail in the multiple integral class. For example, if the region is spherical in nature, so better to move to the spherical polar coordinates. Okay, so x is equal to r sine theta, r sine theta cos phi, y is equal to r sine theta sine pi, z is equal to r cos theta, and theta will vary from 0 to pi, pi will vary from 0 to 2 pi, and r will vary from 0 to the radius of the sphere. And if we are required to find the volume integral on a portion of cylinder, then better to move to the cylindrical polar coordinates. So those coordinates probably have been introduced in the previous classes: spherical polar coordinates and cylindrical polar coordinates. And Cartesian coordinates you already, all of you know. So is it done there?
Yes, sir.
Excuse me, sir.
Yes.
Sir, can we
Yeah.
change the order of integration? Means first dx, then dy, then dz.
No, then that will be difficult. That will be a problem. How will you do? So you have to change the limits then.
Yes, sir.
It is allowed as long as this function is smooth, sufficiently smooth, continuous, then all the derivatives, all the iterated derivatives are equal. So there are some theorems, probably it has been mentioned in the previous class. Um, but you
Sir,
have to
like the
change the
main question
limits.
is in this question, we got only z is equal to x square. So it took this much time, na sir. So if z is equal to x square minus y minus 4 by 4, like that, the complicated will given. So it is hard to calculate at the integration of z with respect to z. So can we change the order?
If you change the order, somehow at some point of time you have to deal with that surface. Okay, normally in textbook problems or in exam problems, the surfaces are given are standard. Either this is paraboloid basically, and or ellipsoid, portion of ellipsoid or portion of cylinder. So those type of regular structures are given, or cuboid. Okay, but if really the surface is complicated, then you have to by just looking at the form of the function, it is difficult to determine the shape. Okay, either we have to resort to numerical analysis or all other surface tracing techniques. Okay, that is normally difficult, and those are avoided in uh, exams or textbook problems. Okay, in textbooks and exams, normally regular curves are given for which we have some regular surfaces are given for which we have a clear idea about the nature of the surface. Okay, like paraboloid, ellipsoid.
Sir, it happened to me once, like calculating the area integral. Once I was doing with another iterated integral form, so answer came 0. And if I just flip the like the limits, then it got uh, calculated. So, sir, that kind of problem it is there. So, but sir, why it is there? Like the
I know,
all
order of integration. So yeah, so sometimes it might be difficult. The function is such that the given integration is with respect to some variable is difficult. Okay, integration with respect to some variable might be difficult. For example, if I give, probably the typical problem is given e to the power x square, something like that, dx dy, and the region is complicated. But if you change the order of integration using the continuity nature of this function e to the power x square, then it is integrable. 2x comes in the beginning and it is perfectly integrable. Okay, so that type of situation is there. It depends on the function actually under consideration. But in this case, this is not the problem, but you can try it with by changing the order of integrations. Okay, but in that case you have to be a bit careful. Okay, for you have to choose the limits very carefully, correct limits rather.
Sir, so means in this case we are projecting in XY plane, and in that case we have to project in YZ plane, like that, sir.
It depends actually. If you project on YZ plane, then yeah, the whole scenario you have to depict
Sir,
on YZ
sir,
plane. Yeah, it can be done.
sir,
YZ plane, yeah. Yes.
sir, second question, sir, how can proceed, sir?
Second question.
Yes,
Similar.
sir.
It is plane. Plane is easiest. Plane is the easiest thing. So yeah, so region will be similar, no? Similar to problem 1. Only the equation of the plane has been changed.
Sir,
And
is divergent or not, sir?
divergence. This is not divergence. Divergence means
Sir,
nabla dot that vector. This is, you will get a
yes,
vector
nebula
here.
dot F, sir.
This is not nabla dot f. This is just f. You will get a vector in this case. Okay. In the definition you see two types of volume integrals I have defined. One
Sir,
is involving
sir.
the vector. Another is involving the scalar. Yes.
Sir, the answer of the second question is a vector, sir.
Yeah, answer will be a vector. See, vector is multiplied with the elementary volumes. You look at the form, you should get a vector. If the function is scalar and we are considering this type of volume integral phi dx dv, then you will get a pure number. But if the function defined in the region is vector, and we are considering this type of vector times the elementary region, this is my integration element, then we'll get a vector. Here in the second case we will get a vector. Answer is like problem number 3. Region only has been changed actually, but type of volume integral is similar here in both the cases, problem number 2 and 3. Okay. Well, so yeah, so Green's theorem in a plane. Okay, so
Sir,
now
show the
there is
previous slide, sir.
this one.
Yes, sir. Yes.
Region, should I discuss how to determine the limits?
No, sir. I only want to screenshot the question answer.
Yeah, you can download it. It is already uploaded. Okay, so Green's theorem. Green's theorem in a plane. So here is a connection between line integral and double integral. Okay, in a plane, we are within a plane. So what we have in our hand, we have a closed regular curve. It is not like something like the number 8. It is a regular closed curve. It is not like this. Okay. So if we have this type of curve, then we have to use Green's theorem separately. Okay, but that is not the case. So in our case, curve is something like this, and okay, curve is something like this. This is simple closed curve, and sense of description is positive. Okay, that means anti-clockwise sense. There is no ambiguity to determine the positive sense of description of the curve C. And we have two continuous functions, P and Q. And having continuous derivative, we need to differentiate. Therefore, the derivatives should exist and they should be continuous. So these are the minimal requirements. So then this line integral P dx plus Q dy, P dx plus Q dy over the closed curve C is equal to the double integral over the region R of the function del Q del X. First, second function is appearing del Q del X minus del P del Y dx dy. So here I have discussed a proof of this theorem. You can have a look at it. This is quite simple.
What is R?
R is the region enclosed by this C. This is your R. This is your C. This curve is C and which is enclosing a region R. So double integral we have to take over the region R, and line integral will be on this curve C in positive sense. So proof I am not discussing. It is given over here. And now this is the vector form. Basically, if we have, if we write A is equal to, Mn I have introduced. So you see already written A vector is equal to Mi plus Nj. It has two components, and this dr differential vector is dxi plus dyi. Then the left hand side of the Green's theorem can be written as p dx plus q dy. You see mn, you replace p and q by mn. So I should not have changed the notation. Anyway, so mi plus nj, and you take the dot product of this with dr, you will get m dx plus n dy, and we have to take the integral over the closed curve C, closed simple curve C, which is enclosing a region R, and sense of description of C is positive. And then cross product of this nabla operator. This is what is your nabla? We already know this is I del del x plus j del del y plus k del del z. And if you take the cross product of this with A, so k, this part is 0 because we are within a plane. And if you take the cross product of this and take the kth component, cross product of this and take the kth component, you will get del m del y, del n del x minus del m del y, and this dr is equal to dx dy. So this is just a vector form, but this is the convenient form we will be using frequently. So p dx plus q dy. Yes.
The C represents the closed curve.
C represent the closed curve, and sense of description is positive. That means anti-clockwise. Okay. And R is the region enclosed by C. Okay.
Yes, sir.
So K is the Z component.
K is the unit vector in the Z component. Yeah. Unit vector. Here is the dot product. You calculate this one. So I think let me show you how this is coming. Right hand side is coming. Right hand side. So what is the vector form? C A dot dr. This is equal to double integral of A dot k. That means third component of this vector we have to consider, and then dr is equal to dx dy. So let us take A is equal to pi plus qj, and dr, then this is equal to dxi plus dyj. So therefore left hand side you see A dot dr, this is equal to p dx plus q dy. And what is your this cross product of this nabla with A? This is equal to I j k del del x del del y del del z, and A has two components only, p q, and there is no third component, 0. And then you take the kth component. So what is ijth component will not be necessary in this case. I will take the kth component of this.
So why is the kth component only?
So this is basically an effort to write the or represent the Green's theorem in vector form. Okay, and it turns out that if you take the dot product of this quantity with k, you will get the desired number, a desired function.
Sir, what is the significance of this theorem? I cannot understand what it does.
It depends actually. For example, if you want to, so let me, it is not here. So it can have different kind of significance. This integral, this line integral a dot dr. For example, if a is the force field and dr is the dr is the displacement, infinite small displacement, then this integral will represent the work done by the force field in moving a particle from one point on this closed curve. So in moving a particle from a point on this closed curve and encircling the curve and coming back to this point. Okay, so the total work done by the force field is given by this integral. And sometimes what can happen, evaluation of this line integral is difficult. It might happen depending on the nature of the function. So then what we will do, we'll convert this to a double integral using this formula. And this double integral will might help you to determine the work done. And in so what can possibly be the other, if A is force field, then this will give us the work done, and this can be calculated by this. So that is the mathematically, this is basically, it depends. We know this relation, whatever is easier we will use to calculate.
Yes, sir. The can't it be used for the reverse? Like the surface integral is difficult to find, so
both way. If the surface integral is difficult, then we'll move to line integral. Whichever is easier, we will calculate. So here you can see you will get del q del x minus del p del y. And if you take the, so plus you have something plus j into something,
0.
but is it 0? No, there will be something. Del q del minus del
Yes,
q
sir.
del z.
Minus del q by del z, sir.
Yeah. Minus del q by del z you will get. So therefore we will take the component, kth component, and we will get the equivalence with the Cartesian form. Okay, so now let us verify Green's theorem for this particular problem in the plane. So C is the closed curve of the region bounded by y equal to x and y equal to x square. So let us use Green's theorem. What is your Pxy? Yes.
Pxy plus y square, sir.
Yeah, P
Q
is equal
to x square.
Q is equal to x square. So let us try
Minus
to
1 by 20, sir.
Minus 1 by 20. So I have written the answer here.
Yes, sir.
So we have to calculate C xy plus y square dx plus
X square.
X square dy and y equal to x, y equal to x square plus x square dy. So we have to evaluate we have to check the verify Green's theorem. That means both sides we have to evaluate and check whether they are coming to be equal or not. So Pxy, this is equal to xy plus y square, and q, that is equal to x square in this case. And we have to have these functions as well, del p del y, that is equal to x, and del q del x.
2y.
This is equal to 2.
Sir, x plus 2y na, sir.
X plus 2y, very good.
2y.
Yes.
Yes, sir.
Okay, so now what is our C? Let us have a look. This is your straight line, y equal to x and y equal to x square, 0x y. y equal to x square means for each value of y, we'll have two different x's, right? It will go above or
below, sir.
Below,
One
sir.
below.
And symmetric about y, sir.
Below, sir. Yes, sir.
symmetric about y axis.
Below the line.
Then it will
Yeah,
Yes,
so
sir.
y equal to x square, and we will move in anticlockwise sense, and this is our R region. So what is this point? That is probably 1 1 and
1,1, sir.
yeah, 1 comma 1, and
1,
let us give
1.
the names here. So let us give the names of the strategic points A. So let us suppose B, and this upper part is C. So therefore this C, so as we are moving, let us see x y plus y square dx plus x square dy, and this we will divide into two parts. So first part will calculate the integral on this curve OBC, that is on y equal to x square xy plus y square dx plus x square dy plus
Yes.
ACO.
Yes.
CO, same function.
so why
X,
Sir, 2x
yes,
minus x minus 2y.
Sir, OBA.
Integration of 0 to 1 x square to x, sir.
that I will do. That I will do. Let me first write in terms of this.
OBA. OBA, sir.
Yes, sir. First term will be
OBA. Yeah. This will be OBA.
Yes,
OBA, sir, OBA.
Yeah, today I am doing lots of mistake. But it is good to do mistake, you know, so that yeah.
Yes, sir.
You are detecting. So that means you are following.
But not in exam, then we will lose.
Yes,
Oh,
sir.
yeah. In exam we are flexible, and especially as far as online exam is concerned, you know what happens. Anyway, so on OBA, so now let us focus on OBA. On OBA, y is related to x by this formula. So therefore, this implies dy can be changed to 2x dx. Along this line, we have this simplification, and x is varying from, and
0
x
to 1.
ranges from
0 to 1.
x ranges from 0 to
0 to 1, sir.
and
1, sir.
similarly
0 to 1.
yeah, 0 to 1, and on the other curve ACO,
Y equal to x, that means dy
X
equal
square
to
to
x.
x, sir.
UI is equal to DX.
So y equal to x,
Then
dy
x
equal to
equal to
dx.
dy equal to dx, and x will vary from 1 to 0, you see.
Yes, sir. Anti-clockwise.
Yes, sir.
Yes, sir.
Yeah,
1 to
we have to maintain the sequence actually. So accordingly, we have to fix the limit. Now
Yes, sir.
we can.
So why 1 to 0?
So we are starting from this point A, and at this point, value of x is equal to 1.
So
And
why
then,
this anti-clockwise, sir?
so otherwise, there will be in the proof. You can have a look at it. Otherwise, this equivalence cannot be established if you don't consider this anti-clockwise sense of description. The result of the theorem cannot be established. There will be a sign problem. Okay, so therefore considering anti-clockwise sense of description is necessary in this case.
Then the complete loop is considered.
Yeah, complete
0 to
loop.
1 and
This
1 to
is
0.
yeah, close. If C is not a closed curve, then you cannot connect it with the double integral.
Yes,
Okay.
sir.
So you should get the answers. I think you can evaluate it. You should get the desired result minus 1 by 20. So this is the
Yes,
line
sir.
integral. This is the line integral. Now we will consider. So we need to verify Green's theorem. Yes.
So previous page.
Just a minute. Let me just write this. X plus no, not this one. So we have to find del q del y minus del p del x dx dy. So this one we have to evaluate double integral, and we have to check that whether minus 1 by 20 is coming.
It will be del q del x.
Yeah, so someone was asking for this page.
Yes, sir, done.
Okay, so are you getting minus 1 by 20 after evaluation?
Yes, sir.
Okay. Del q del x, yeah. Del q del x and del p del y. Del q del x del p del y. And what the function, which function are you getting? So that is y plus 2y. No, del q del
X minus 2y, sir. X
Sir,
minus
x
2y.
plus 2y and 2x.
X minus 2y.
Sir, 2x minus x plus 2y.
Achha, so
X minus 2y.
So x plus 2x minus x plus 2y. Okay.
Yes, sir.
2x minus x minus 2y dx dy. So this is equal to R. R is the region enclosed by the closed curve C. So x minus 2y dx dy. So now we have to look at the region once again. Y equal to x.
This is 0 to 1.
So this is y equal to x, and this one is the y equal to x square, and this point is 1 1, and we have to consider this region. So if we look at this region from this side, you see x is varying from 0 to 1.
0 to 1. X
0
square to
1,
x.
and as x is varying from 0 to 1, this lower curve, lower boundary is determined by y equal to x square. So y will vary from x square to
X
square to x. So
X square to
therefore,
x.
yeah, so therefore
0 to 1.
x equal to 0 to 1 dx, this we will
Y to
calculate later. Y
x
equal to x square to x.
X
X minus 2y dy.
Yes.
And this is equal to 0 to 1, and xy minus y square. I think this time I think I am correct.
Yes, sir.
Y x square
Yes, sir.
to x dx. And which function you are getting if you calculate
X to the
the
power 4 minus x
X
to the power
square
q, sir.
minus x cube
X to the
minus
power
x to
4
the power 4
minus x
minus
to the power q, sir.
plus x square.
x to the power x cube minus x to the power 4 minus
minus
no, wait, I have to put, first I have to put the limit x.
Sir.
X square minus x square, so that is 0.
Yes, sir.
Yes, sir.
Yes, sir.
And then
X to the power
minus
4 minus x to the q, sir.
x to the power 4 minus x cube. This is the term which will be
Yes, sir.
written.
Yes, sir.
And we
Then
will
1
get
by
1
5
by
minus 1 by
5
4
minus 1 by
minus
4
1 by 4.
minus 1 by
Then
20.
plus
Are you
minus 1
getting?
by 20.
Yes,
Yes,
sir.
sir. Yes, sir.
So therefore you see we are getting, so
Both side
therefore for
equal.
the, okay, so therefore we can write integration c p dx plus q dy is equal to over r del q del x minus del p del y dx dy. So therefore Green's theorem is verified. Green's theorem is verified. So in this, related to this theorem, there can be two different kinds of problems. Okay, so in one class of problem, use of this theorem is done, and in another class of problem, verification of Green's theorem is required. So only two different kinds of
Show the previous page.
problems are there, and few more problems will be discussed in the tutorial class. So I think yeah, I should stop here today. Let me.
Okay, thank you, sir.
Sir, on
And
Monday there will be class. I mean,
Thank you.
Sir,
previous
stop
classes.
the recording.
Sir,
Sir.
Thank you, sir.
sir, call